Welcome back to QHSE Talks. So picture this. You are sitting at your desk right now, just perfectly still.
Right, probably just staring at a monitor.
Exactly. You aren't lifting heavy doxes, you aren't operating a jackhammer.
Yeah, you're not swinging a sledgehammer or anything like that.
And yet, biomechanically speaking, your muscles are just screaming for oxygen. The blood vessels in your shoulders and neck are acting like, well, tight and tourniquet.
Oh yeah, just totally starving the tissue.
Right, and lactic acid is pooling in these tiny microscopic pockets. Now, you might feel fine right now, but your body is quietly keeping a ledger of all this invisible damage.
It really is. It's logging every minute.
So whether you are an aspiring safety professional who's meticulously prepping for your ASP exam, or you're just insanely curious about why your back screams at you after a supposedly easy shift at the computer, this session of QHSE Talks is custom tailored for you.
Absolutely. Today, we are looking at those invisible physical forces that basically dictate how our anatomy interacts with our work environments every single day.
Yeah, and it's a dynamic that impacts literally every human being who performs a job, but somehow it remains one of the most misunderstood aspects of occupational health.
Oh, for sure. I mean, the human organism is remarkably resilient.
Right.
It's capable of incredible feats of endurance.
Right.
But it operates within very specific, non-negotiable biomechanical parameters.
Right.
And when a workplace is designed without respecting those parameters, well, the resulting structural failures in the body are painful.
And financially devastating, right? To both the worker and the company.
Exactly. And the tragic part is that they are entirely predictable and preventable.
Which is crazy when you think about it. So our mission on this edition of QHSE Talks focuses squarely on ASP Exam Domain 3, Topic 2.
Right, the section on identifying ergonomic risk factors.
Yes, and if you look at the certification blueprint, this single domain makes up 8% of the entire exam. That is huge.
It's a massive chunk. You really have to know this stuff inside and out.
So we are breaking down the 4 main pillars you need to master to effectively evaluate any workspace. That's repetition, force, awkward and static postures, and a final category for other environmental stressors.
Like vibration and temperature conditions, right?
Yeah. But before we get into the granular biomechanics, we have to establish the foundational philosophy here. Because, ergonomics is a buzzword, right? It gets slapped on everything.
Oh, definitely. Expensive keyboards, weirdly shaped chairs.
Exactly. So what is the actual scientific discipline we are talking about here?
Well, the golden rule of ergonomics, the absolute core principle every safety professional has to internalize, is that it's the scientific study of work based on adapting the job to the person.
Okay, adapting the job to the person, not the other way around.
Right, rather than forcing the person to fit the parameters of the job. That's the key difference.
That makes sense.
It's an applied science. We're measuring the stress and strain on the human body during work-related tasks.
So the ultimate objective is to, just systematically reduce the risk of long-term injuries?
Exactly. By figuring out what specific mechanical tasks or repetitive motions lead to tissue failure, and then engineering the workplace conditions to accommodate the natural limitations of the human body.
I feel like that is a massive paradigm shift. Think about the historical context of labor.
Oh, this is brutal.
Right. For centuries, the mindset was basically that the worker just needed to be tougher. If you got hurt, it was a personal failing.
Blame the victim, essentially.
Yeah, and we still do this today. We blame our bodies. Someone says, oh, I have a bad back, or my wrists are just weak.
Like it's their own fault.
Right, but this discipline suggests something entirely different. It suggests that the workspace itself might be fundamentally antagonistic to human anatomy.
That's a great way to put it. We are blaming the worker for what is essentially an engineering failure.
Yeah, failure by whoever designed the assembly line or the office cubicle.
Exactly. The historical mindset was absolutely a blame the victim mentality. Like, if a worker has to constantly bend over at a severe 15-degree angle to lift a 40-pound box,
just because a facility planner decided to store pallets directly on the concrete floor.
Right. The resulting herniated lumbar disc isn't because that worker has an intrinsically bad back.
Right, it's the environment.
It is because the geometric layout of the workstation forced them into an extreme, structurally compromised posture, and then combined it with a heavy compressive load.
So when we assess physical ergonomics, we are evaluating human anatomical dimensions and physiological recovery rates.
Yes, and biomechanical leverage, as they all interact with the physical activity. We measure the angles of working postures, the physics of material handling, the cycle times.
It sounds like we are basically diagnosing the environment.
That's exactly it. The worker is just the indicator light on the dashboard showing us that the system is broken.
Wow, the indicator light. I love that. I want to focus on that for a moment because it brings us to the stakes of this conversation. Why is this topic weighted so heavily on the ASP exam?
Well, it comes down to the frequency and cost of these injuries.
Right. Why do safety professionals spend weeks analyzing how high a desk is or the exact diameter of a screwdriver handle? We need to talk about musculoskeletal disorders, right? MSDs?
Yes, MSDs and cumulative trauma disorders, or CTDs.
Because this isn't about dramatic workplace accidents, is it?
Not at all. In occupational safety, when we think of hazards, we usually picture acute events. A worker falling from a scaffold, a chemical splash, a forklift collision.
Right, sudden, obvious things.
Yeah, instantaneous transfers of energy resulting in sudden trauma. But ergonomic hazards are insidious. They cause damage through a completely different mechanism.
So it's more about microtraumas.
Exactly. Microtraumas accumulated over extended periods. It's the slow, progressive, microscopic wear and tear on the connective tissues.
Like the tendons and ligaments.
Tendons, ligaments, the synovial sheaths, the muscles, the peripheral nerves, and the vascular system. It just grinds them down.
So the hazard isn't the single heavy crate you moved on a Tuesday afternoon. The hazard is the 10,000 medium-sized crates you moved over the span of 5 years.
Yes. The body is keeping score, even if you don't feel it right away.
Let's trace the pathology of one of these, like a specific, really common cumulative trauma disorder.
Carpal tunnel syndrome is a perfect example. It gives a really clear window into how these injuries develop.
Okay, so walk me through it. What is the carpal tunnel anatomically?
The carpal tunnel is an actual physical passageway in your wrist. The floor and sides are made of carpal bones, and the roof is a rigid band of connective tissue.
Wait, what's that band called?
It's called the transverse carpal ligament, and it creates a very tight, confined space.
Ah, okay.
So running through this tiny bony tunnel are 9 flexor tendons that control your fingers, plus the median nerve, which gives sensation to your hand.
9 tendons and a nerve all packed into one little bony tube.
Exactly. It's crowded in there.
And so when you introduce repetitive, stressful wrist motions, like, say, bending the wrist up and down thousands of times a day on a keyboard, what happens inside that tunnel?
Well, the constant mechanical friction of those tendons sliding back and forth causes inflammation.
Right, they're rubbing against each other.
Yeah, and the synovial sheaths surrounding the tendons get irritated and start to produce excess fluid.
And because the tunnel is made of bone and rigid ligament, I'm guessing it can't expand.
Exactly. It cannot expand to accommodate this swelling, so the pressure inside the tunnel rapidly increases.
Yikes. So it just builds and builds.
Yes, and that fluid buildup, or the actual thickening of the irritated ligaments, starts to physically crush the median nerve against the bone.
Oh man, that sounds agonizing. And nerve compression is what sends that constant message of pain to the brain.
That's the one. And our source materials note that the typical symptoms of carpal tunnel syndrome include severe tingling in the thumb and fingers, a loss of grip strength, and this is key intense night pain.
Night pain. Wait, workers report that it literally wakes them from a dead sleep?
Yes, frequently. They find themselves hanging their arms off the side of the bed or vigorously shaking their hands just to restore blood flow and get a moment of relief.
That is wild. Why does it happen at night, though?
Well, when we sleep, our blood pressure naturally drops, and we often subconsciously curl our wrists inward.
Oh, which just further compresses that already swollen tunnel.
Exactly. And if a worker continues to perform the exact same job under these conditions, the median nerve undergoes demyelination.
Demyelination, meaning the protective coating of the nerve is destroyed.
Yes. And that results in permanent numbness, muscle atrophy at the base of the thumb, and a lifelong disability.
So the injury isn't an accident. It's merely the final catastrophic symptom of a prolonged exposure to poor design.
That is perfectly stated.
I am thinking of a mechanical analogy here. It's like a car engine running with a slow oil leak.
Okay, I like where this is going.
If you just take a quick 5-minute trip down the street to the grocery store, you probably won't seize the engine, right? The residual oil protects it.
Right. Short duration, low risk.
But if you get on the highway and attempt to drive cross-country with inadequate lubrication, the daily compounding thermal friction inside the metal engine block inevitably leads to the pistons fusing to the cylinders.
Exactly. The friction was present during the short trip, But it was the time and the repetition that eventually overwhelmed the system's capacity to dissipate heat.
Yes. So expanding on that mechanical model, the friction in the engine represents the localized mechanical stress on the human tissues.
And to predict exactly when that engine is going to fail, safety professionals utilize a specific conceptual formula to evaluate the risk of an ergonomic task.
Okay, so the risk is not just a single variable.
No, it is a product of three primary multipliers: duration, frequency, and magnitude.
Let's dissect those three multipliers. If I am an ASP candidate walking onto a factory floor, how am I defining these variables when I observe a worker? Let's start with duration.
Duration is simply the temporal measurement. How long is the worker exposed to the specific risk factor during a given period?
Like, are they doing the task for 2 hours before taking a break, or are they locked in for an 8-hour shift?
Exactly. And duration also macroscopically encompasses the worker's tenure. Like, have they been doing this job for 3 months or 15 years?
Got it. And what about frequency?
Frequency measures the repetition rate within that duration. How often is the specific hazardous motion performed?
So, are they reaching overhead to tighten a bolt once every 5 minutes or 45 times a minute?
Right. And finally, magnitude.
Which is the sheer physical intensity of the exposure, right?
Correct. Magnitude asks, how heavy is the object being lifted? How many pounds of pinch force are required to activate the tool? How extreme is the localized vibration?
Or even how cold the ambient air temperature is.
Exactly. All of that falls under magnitude.
This means the danger really lies in the mathematical interplay of these factors.
Yeah, it absolutely does.
Because if you have a task with incredibly high magnitude like lifting a 200-pound engine block, but the frequency is once a year and the duration is 5 seconds.
Well, the body will likely recruit enough muscle fibers to handle it, assuming proper posture, and then fully recover.
Right. But if you have a task with incredibly low magnitude, like clicking a plastic mouse button that requires mere ounces of force, but the frequency is thousands of times a day,
and the duration is decades.
yeah, then you are virtually guaranteed to develop tissue degradation.
Yes. The most dangerous jobs are those that elevate all three multipliers simultaneously.
So to intervene effectively, the safety professional has to isolate the specific ergonomic risk factors driving those multipliers.
That's the core of the job.
And that transition takes us right to the first major risk factor outlined in the ASP exam blueprint: repetition.
The grind.
Right, the grind. We just discussed clicking a mouse or typing, which feels intuitively repetitive. But in the realm of biomechanics and safety engineering, how do we strictly define repetition? It can't just be doing something a lot.
No, it's more specific. In an ergonomic assessment, repetition is formally defined as the time variation of a musculoskeletal load.
The time variation of a musculoskeletal load. Okay, translate that for me.
Practically speaking, the repetitiveness of a task is the cyclical use of the exact same tissue structure, the same specific muscle group, tendon, or joint over and over again.
So when a safety professional reports repetition levels, they must quantify it.
Yes. They record the specific body part engaged, they measure the cycle time of the task in seconds or minutes, and they count the number of discrete movements per unit of time.
Let's break down that phrase, time variation of a musculoskeletal load. Why is the variation over time the issue?
Well, think of a single muscle fiber like a thick rubber band.
Okay.
If you stretch that rubber band once, hold it for a second, and let it snap back, no problem. That's a low-frequency variation.
Makes sense.
But if you pull and release that same rubber band 3 times a second for an hour straight, the rubber actually generates thermal heat.
Right, it gets warm.
And it begins to dry out, it gets brittle, and microscopic tears form along the edges until it snaps. You are denying the tissue the time required to clear metabolic waste and repair the micro tears.
Ah, so metabolic clearance is the limiting factor here.
Yes. Muscles require oxygenated blood to perform work, and they produce metabolic byproducts when they contract.
Like lactic acid.
Exactly. If the cycle time of a task is so fast that the muscle never fully relaxes, the blood vessels remain partially compressed.
So the tissue is starved of fresh oxygen while simultaneously drowning in its own waste products. That is a grim picture.
It is. But our sources point out an incredibly fascinating nuance about repetition.
Oh, what's that?
The concept of highly repetitive is not universal across the human body. The hazard level depends entirely on which body part is doing the repeating.
Oh, right. So a frequency that destroys a shoulder might be completely fine for a hand.
Exactly. This introduces the science of anthropometrics and functional anatomy.
Because of evolutionary biology. Really.
Yes. Different muscle groups are designed for vastly different functions and therefore can sustain vastly different repetition rates before the injury threshold is crossed.
So like the flexor and extensor tendons that control our fingers.
They're designed for near constant, low-load dynamic movement. They can handle an astonishing amount of repetition.
But conversely, the massive, heavy structural muscles of the lower back, the erector spinae, they're designed for stability and postural support.
Right, our ancestors evolved using their hands continuously for tool-making and gathering.
We didn't evolve to continuously hinge our entire upper body weight at the lumbar spine hundreds of times an hour. The back is a stabilizing column, not a high-speed hinge.
Exactly. So an ASP candidate evaluating a task that requires 40 finger flexions per minute might deem the repetition risk acceptable.
But if the task requires 40 trunk flexions bending at the waist per minute,
that is an immediate catastrophic red flag, requiring urgent engineering controls.
Okay, I want to push back on the idea of repetition as a standalone hazard for a second.
Sure.
Let's say I am sitting in an ergonomically perfect chair. My posture is flawlessly neutral. My arms are perfectly supported. And I am simply tapping my index finger on a desk.
Okay, perfect posture, low force.
Right, minimal force, perfect posture. If I do that 10,000 times, will I inevitably develop a cumulative trauma disorder just because of the sheer math of the repetition? Like, does repetition act alone, or does it need an accomplice to really cause damage?
That's a great question. In a strictly theoretical environment, highly repetitive actions performed in a completely neutral posture with virtually zero external resistance carry a relatively low risk of injury.
So my finger tapping is probably fine.
Under those ideal conditions, yes. The body's vascular system is highly efficient at supplying oxygen and removing waste, keeping pace with the demand.
But I'm guessing ideal conditions rarely exist on a factory floor.
Exactly. The reality is that pure repetition rarely exists in the workplace. The danger of repetition is that it acts as a massive physiological amplifier.
It multiplies the damage of other ergonomic sins.
Precisely. The injury risk curve doesn't just go up linearly, it spikes exponentially when repetition is combined with other risk factors.
So if you take that finger tapping motion, but now the wrist is bent upward at a sharp angle, an awkward posture.
Now the tendon is rubbing against the bone with every single tap.
Yeah.
Or if you add force, requiring the finger to press a stiff, resistant button 10,000 times.
Right, it's a whole different game.
Studying repetition completely in isolation will almost always result in an underestimation of the true injury risk. You just cannot assess repetition without simultaneously assessing posture and force.
Well, if repetition is the amplifier, we need to look at what it is amplifying. That brings us to the second major risk factor on the exam blueprint: force.
Right.
When a layperson hears workplace force, they immediately picture a warehouse worker trying to deadlift a refrigerator or pushing a massive cart.
Sure, macro-level force.
But biomechanical force is much more pervasive and subtle than just heavy lifting, isn't it?
Absolutely. Force in this context refers to the magnitude and intensity of the mechanical load that a specific muscle or group of muscles must exert to satisfy a job demand.
So heavy lifting and lowering are the classic, easily identifiable scenarios. They impose massive compressive forces directly on the spinal discs.
Right, but force also encompasses carrying, pushing, and pulling tasks. Furthermore, force applied by the upper limbs is incredibly common and often overlooked.
Like gripping a tool.
Yes. Tasks that require gripping a tool, pinching a small component, or simply holding a heavy object steady.
You know, that brings up the issue of gripping, and one of the most counterintuitive facts I discovered in the source material, it's what we can call the glove effect.
Oh, the glove effect is fascinating.
Right. If you are a safety manager, your first instinct when you see a hazard-like sharp metal edges on a fabrication line is to issue personal protective equipment.
Naturally. You hand the worker a thick pair of leather or Kevlar gloves to prevent lacerations.
But the texts highlight that wearing gloves actually increases the required hand grip force by anywhere from 7% to 28%.
Depending on the thickness, the material, and the fit of the glove, yes.
That is wild to me. It represents a classic conflict in safety engineering.
It really does.
Yeah.
By introducing administrative control to mitigate a laceration hazard, you inadvertently amplify an ergonomic hazard.
Because when a worker dons a glove, the thick material creates a physical mechanical barrier that resists the natural flexion of the finger joints.
The muscles in the forearm now have to work against the stiffness of the glove itself, just to close the hand.
But there's a neurological component too, isn't there? It's not just the physical stiffness of the leather.
The neurological component is arguably the larger issue. The human hand is packed with sensory receptors that provide constant tactile feedback to the brain.
Like, when you pick up a glass of water, your brain subconsciously calculates the exact minimal amount of pinch force required to keep the glass from slipping through your fingers without crushing it.
Yes. But when you wear a thick glove, you sever that tactile feedback loop. The central nervous system can no longer accurately feel the surface friction or the weight of the object.
And because the brain is blind to the object, it panics, it overcompensates.
Exactly. To prevent the object from dropping, the motor cortex commands the forearm muscles to exert significantly more grip force than is mathematically necessary.
It is exactly like driving a car that has suddenly lost its power steering.
That's a great analogy.
You don't realize how much harder your hands are gripping the steering wheel, how much your forearms are flexing, and how your shoulders are bracing just to muscle the car through a simple turn.
Right, your body is recruiting vast amounts of extra muscle fiber just to overcome the newly introduced resistance in the environment.
So if you force a worker to wear poorly fitted, bulky gloves for an 8-hour shift while operating a hand tool,
that 28% increase in continuous force application is going to obliterate the endurance of their flexor tendons.
that is incredible.
And this leads us to correct a widespread misconception regarding force. Many people assume that force-related injuries only stem from a single catastrophic overexertion.
Like a massive lift that immediately exceeds the tensile strength of a ligament, causing it to snap.
Right. While acute tears certainly happen, the reality of occupational health is that moderate force, applied continuously over an extended period, is a primary driver of cumulative trauma.
Just a moderate force over time.
Consider a worker simply maintaining a tight, static grip on a vibrating power drill for 6 hours a day. The absolute force is moderate, maybe only 10 pounds of grip pressure, but the duration is massive.
Wow. Okay, so we have established repetition as the frequency of movement and force as the mechanical effort required. But here is the critical link.
Go ahead.
You cannot exert force, nor can you perform a repetitive motion without putting your skeletal frame into a specific spatial arrangement.
The geometry of the body.
Right. The way your bones and joints are aligned dictates the leverage your muscles have, which brings us to the silent, invisible hazard that plagues everyone from roofers to accountants. Awkward and static postures.
Posture simply describes the angles and positions of the body's joints while performing a given task.
And the fundamental goal of ergonomics is to design work so that the body can remain in a neutral posture, right?
Yes. A neutral posture is the alignment where the body is optimally balanced. In this state, the muscles, tendons, and skeletal system have maximum mechanical advantage.
Basically, the muscles don't have to fight the body's own geometry.
Precisely. The joints are resting in their mid-range of motion, placing the least amount of mechanical stress on the surrounding tissues.
So what constitutes an awkward posture then?
An awkward posture is any significant deviation from this neutral alignment. When you bend a joint to its extreme range of motion, you are physically stretching the tendons and ligaments on one side while severely compressing the tissues on the other.
And that stretching drastically reduces the tissue's tolerance to withstand external force.
Yes. Extreme awkward postures are highly hazardous because they inherently weaken the joint, they pinch off blood vessels, and they require the muscles to fire at a much higher intensity just to hold the limb against the pull of gravity.
Let's give the listener some concrete visual examples of these awkward postures. If I'm taking the ASP exam, I need to be able to spot these immediately on a hypothetical worksite. The sources list several highly common destructive postures. One that stands out for office workers is reaching for a computer mouse that is placed on a different vertical level or pushed far away from the keyboard.
That forces the shoulder into constant outward rotation and elevation. It's terrible.
What are some other classic examples?
Reaching above shoulder height is a massive hazard. You see this constantly in the trades. Electricians wiring overhead fixtures or warehouse workers pulling stock from top racks.
Because the shoulder joint isn't meant for that sustained load.
Right, it trades stability for a wide range of motion. When you work with your hands above your head, you compress the rotator cuff tendons against the acromion bone, leading to severe impingement syndromes.
Okay, what else?
Reaching behind the torso is another critical one, placing extreme rotational torque on the shoulder capsule.
What about the hands and wrists? We talked about carpal tunnel.
In the wrists, awkward postures include ulnar or radial deviation, which is bending the wrist sharply inward or outward while trying to grip.
Oh, like when you type with your wrists angled out?
Exactly. We also look for excessive palmar flexion, pointing the hand down toward the floor, or extreme extension, pointing the hand up toward the ceiling like a traffic cop signaling stop.
And when the wrist is bent in these ways, the flexor tendons have to grind around the bones like a rope being pulled sharply around a jagged corner.
That's a perfect visual. And perhaps most dangerously, we look at the spine.
Oh yeah, the back.
Twisting the lower back, known as trunk rotation, especially while lifting or carrying a load, is the primary mechanism for catastrophic spinal injury.
I want to focus on that spinal twisting for a second. The architecture of the human spine is basically a stack of bone spools separated by jelly-filled discs.
Yes, the intervertebral discs.
It is engineered to handle vertical downward compression incredibly well. Like, you can carry a heavy yoke across your shoulders if your spine is perfectly straight.
It's very strong in pure compression.
But the moment you introduce torsional rotation, twisting your shoulders while your hips remain locked forward, you are wringing out those spinal discs like a wet towel.
Wringing it out, yes.
And if you add a heavy load to that twisting motion, the pressure on the outer wall of the disc is immense, leading directly to herniation.
It is a recipe for mechanical failure.
Uh-oh.
But we must address a crucial distinction that often confuses people evaluating posture. The difference between dynamic and static work.
Okay. We intuitively understand that moving awkwardly while lifting is harmful, but what happens when the body isn't moving at all?
This is where we get into the physiology of sitting still. Muscle effort is categorized as either dynamic or static.
Dynamic work involves rhythmic movement, right? The muscle actively contracts to move a bone, and then it relaxes. The joint moves through its intended range of motion.
Exactly. Static work involves prolonged, sustained muscle contraction where the body, or a specific joint, is held completely immobilized in one position for an extended period.
And this brings up an incredibly counterintuitive physiological reality from our sources.
It really does.
A person holding absolutely still, performing seemingly low-effort static work, like a surgeon holding a retractor or a programmer hovering their hands over a keyboard, they can actually experience significantly faster, more severe muscle fatigue than someone performing dynamic physical labor, like walking or cycling.
It's true.
Wait, hold on. I want to make sure the listener really grasps this. You are telling me that a guy casually walking around a warehouse floor carrying 10-pound boxes is actually doing less physiological damage to his muscle tissue than I am right now, simply holding my neck and arms rigid while I stare at a computer monitor.
Essentially, yes.
That defies basic common sense. Walking burns more calories. How can sitting still be more exhausting to the tissue?
It comes down to cellular respiration and vascular plumbing. When a muscle is engaged in dynamic work, the alternating sequence of contraction and relaxation acts as an internal pump.
Okay, a pump.
When the muscle relaxes, the blood vessels open wide, allowing oxygen-rich arterial blood to flood the tissue. When the muscle contracts, it physically squeezes the veins, pumping the deoxygenated blood and metabolic waste products back toward the heart.
So the movement itself sustains the muscle's energy supply. The dynamic movement is its own life support system.
Precisely. But during static work, that pump is broken.
Because there's no relaxation phase.
Exactly. When a muscle is forced into a continuous, sustained contraction to hold a posture, the muscle fibers physically clamp down on the capillary beds running through them. It acts exactly like a localized tourniquet.
Wow, so the blood flow is severely restricted or entirely occluded.
Which means no fresh oxygen is getting in and no waste is getting out.
And without oxygen, the muscle cells are forced to switch from aerobic respiration to anaerobic respiration to generate energy.
And a byproduct of anaerobic respiration is the rapid accumulation of lactic acid and hydrogen ions within the muscle tissue. The localized pH level drops.
Which is what triggers the pain receptors, causing that deep, acute, burning ache of muscular fatigue.
Right. Because the blood flow is restricted by the static contraction, the body cannot flush the acid away.
So under similar workload conditions, static work forces a higher systemic heart rate, consumes energy less efficiently, and mandates significantly longer recovery periods than dynamic movement.
That's the cruel irony of office work.
Think about the physical reality of it. If you are sitting in a chair without proper lumbar support, your core and lower back muscles are locked in static contraction just to keep your torso upright.
Yes.
If your keyboard is too high, your deltoids and trapezius muscles are performing static work to hold the weight of your arms suspended in the air.
And if your monitor is too low, the posterior neck muscles are continuously firing just to prevent your heavy skull from dropping forward onto your chest.
You feel exhausted at the end of a desk shift, not because you did heavy lifting, but because multiple muscle groups spent 8 hours suffocating under their own static tension.
The static component is almost universally the limiting factor in endurance for any job. In a data entry role, the fingers are performing rapid dynamic work, but the fingers rarely fatigue first.
Right. It is the neck, the shoulders, and the upper back.
Yes. The structural muscles forced into agonizing static holds to provide a stable platform for the dynamic movement of the fingers. They are the ones that fail and cause chronic pain.
Okay, let's summarize our diagnosis so far. We have analyzed the repetition, which is how often the body moves. We have the force, how much physical effort is exerted, and the posture, the geometric alignment of the joints.
Right.
But the human body does not operate in a sterile vacuum. It exists within a physical environment, and that environment is constantly actively imparting stress onto the biological system.
Which brings us to our fourth pillar on the ASP exam blueprint. Other stressors, starting with vibration and mechanical contact.
These environmental variables act as insidious multipliers to the biomechanical risks we have already established.
Absolutely. Right? Let's examine vibration, which is a massive hazard in industrial, construction, and agricultural settings. Occupational vibration is bifurcated into two main categories. Hand-arm vibration, known as HAV, and whole-body vibration.
Our sources provide some chilling historical context for hand-arm vibration. It discusses a pathology medically known as Raynaud's phenomenon. But historically, stonecutters and miners who operated pneumatic drills for 12 hours a day referred to it simply as dead fingers. That paints a vivid, gruesome picture.
It really does.
What is the actual mechanism of injury occurring inside the hand to cause that?
Well, prolonged exposure to high-frequency, localized vibration unleashes a devastating two-pronged assault on the hand. First, there is the raw mechanical damage.
Right, just the shaping itself.
Yeah, the intense, rapid oscillation stretches and tears the delicate ligaments in the wrist and degrades the cellular structure of the muscle fibers, leading to a profound loss of grip strength.
And the second prong?
The more insidious damage is vascular and neurological. The vibration physically traumatizes the endothelial lining of the tiny capillaries in the fingers.
Okay.
This trauma causes the blood vessels to violently spasm and collapse inward, entirely shutting off the blood supply to the digits.
So the fingers literally blanch. They turn stark, ghostly white because they are completely devoid of blood.
Yes. The worker suffers severe numbness, deep aching pain, and a total loss of fine motor dexterity.
And this vascular collapse triggers a secondary mechanism that circles back to our earlier discussion on force. It's a phenomenon known as the vibration reflex, right?
Exactly.
Explain the reflex. How does vibration trick the brain?
Inside your hands are specialized nerve endings called Pacinian corpuscles that detect pressure and vibration.
Pacinian corpuscles, got it.
The intense vibration of a power tool overstimulates these nerves until they go entirely numb. Because the hand is now numb, the worker loses all tactile sensation of the tool handle.
Just like the glove effect.
Yes. The subconscious motor cortex senses that the tool might slip out of the numb hand. To prevent this, the brain automatically commands the forearm muscles to grip the tool significantly harder.
It's the glove effect all over again, but induced by nerve trauma instead of leather.
Exactly. The worker is entirely unaware that they are overgripping. This vibration reflex drastically inflates the static muscle load.
So the vibration itself physically crushes the blood vessels, and then the resulting subconscious overgrip forcefully squeezes off whatever meager blood flow remains.
It is a vicious, self-perpetuating cycle of tissue strangulation. The National Institute for Occupational Safety and Health estimates that over 1 million workers who regularly operate vibrating hand tools are at severe risk for these permanent vascular injuries.
That covers localized vibration, but what happens when the entire body is vibrating? The sources specifically highlight heavy machinery operators and long-haul truck drivers in the context of whole-body vibration.
Whole-body vibration involves the low-frequency mechanical oscillation of the entire skeletal structure, internal organs, and central nervous system.
The texts draw a technical distinction here between free vibration and forced vibration, right?
Yes. Free vibration is an object vibrating at its own natural frequency. Force vibration is an external force, imposing a continuous oscillation onto an object.
So truck drivers are subjected to relentless forced vibration.
Absolutely. The mechanical energy from the road surface is transferred through the vehicle's tires, up through the stiff suspension through the seat, and directly into the driver's pelvis and spine.
The human spine evolved to act as a shock absorber for walking and running, which are intermittent impacts. It did not evolve to withstand a continuous low-amplitude, high-frequency hum for 10 hours straight.
No, it didn't. That constant mechanical shaking accelerates the dehydration and degeneration of the intervertebral discs.
Wow.
It also induces profound central nervous system fatigue, making it highly dangerous for them to be operating a multi-ton vehicle.
Okay, moving from vibration to another physical stressor, let's look at mechanical contact stress. This sounds straightforward, the body physically hitting something, but how does this manifest as a long-term ergonomic hazard?
Local contact stresses occur when hard, unyielding, or sharp objects are pressed continuously or repeatedly against the soft tissues of the body.
Give me an example.
A textbook example in maintenance or construction is a worker using the heel of their hand as a makeshift hammer to knock a tight pipe fitting into place, or forcefully striking a wrench to break a rusted bolt loose.
The anatomy of the palm is complex too. You have a dense network of nerves and superficial blood vessels located just millimeters beneath the skin.
Right. Striking that soft tissue against solid steel causes immediate localized vascular bruising and nerve confusions.
But the safety professional must also look for passive contact stress, which is rampant in office and light assembly environments.
Yes, passive contact is everywhere. Visualize a worker resting the soft, fleshy underside of their forearms or the delicate carpal tunnel area of their wrists directly against the hard, sharp 90-degree edge of a desk while they type or manipulate small parts.
The actual weight of the worker's arm is using that desk edge like a dull knife blade, continuously pressing into the tissue.
That passive, constant mechanical compression physically pinches the ulnar and median nerves running down the arm and compresses the veins, returning blood to the heart.
Over an 8-hour shift, day after day, that seemingly benign contact point creates significant neuropathy and inflammation.
It really is remarkable how a completely stationary, inert object like a desk edge becomes an active biological hazard, purely based on how human anatomy drapes across it.
It really is. But physical impacts aren't the only environmental variables. The ambient atmosphere of the room itself alters biomechanical performance.
Yes, which leads us to the second half of our other stressors category: temperature, lighting, and noise. Let's delve into temperature, specifically cold environments.
Okay, ambient temperature. How does that have a profound, immediate impact on the physiological cost of work?
Well, when the human organism is exposed to cold environments, the autonomic nervous system initiates a survival response to maintain core body temperature. It triggers massive peripheral vasoconstriction.
Peripheral vasoconstriction, meaning the blood vessels in the extremities, the hands, arms, and feet, narrow significantly.
Yes, shunting the warm blood away from the skin and limbs to protect the vital organs in the torso.
And based on everything we have discussed about oxygen supply and waste removal, intentionally reducing blood flow to working muscles is the genesis of ergonomic injury.
It creates a cascade of biomechanical failures. When muscles and tendons are cold and deprived of optimal blood flow, the synovial fluid thickens.
So the tissues become stiff and lose their elasticity.
Exactly. Because the muscles are stiff and operating inefficiently, the worker instinctively exerts significantly more force to accomplish the exact same task they would perform easily at room temperature.
And this increased demand for force generation further exhausts the already oxygen-deprived muscles.
Right. So if a worker is stationed in a refrigerated meat processing plant, the hazard profile is staggering.
They are enduring the cold, which restricts blood flow. They are performing the highly repetitive motion of slicing meat. They are exerting force to cut through bone. And they are likely in an awkward posture, reaching across a moving conveyor belt.
All four major risk factors are amplifying each other in real time.
And it's vital to recognize that this isn't limited to industrial freezers, right?
Oh, not at all. An office worker can experience the exact same localized physiological degradation if they happen to sit directly beneath an overhead air conditioning vent that blows chilled air continuously onto their neck and shoulder.
Because the trapezius muscles will involuntarily tense and contract in response to the localized cold, initiating a state of static muscle fatigue.
Which results in severe neck pain and tension headaches by the afternoon. This physiology is exactly why athletes perform dynamic warm-ups before exertion. They are artificially dilating the blood vessels to prepare the tissues for mechanical loading.
Now, I have a theoretical question regarding this.
Sure, go for it.
We are focusing heavily on the external environment acting upon the worker. But do the personal, off-the-clock lifestyle choices of the individual actually alter how their body metabolizes these occupational stressors?
That's a really interesting point.
Like if I put two workers of the same age and build in the exact same cold room operating the exact same vibrating tool, are their injury risk profiles identical?
They are absolutely not identical, and this represents a critical layer of complexity for the occupational health professional. An individual's physiological tolerance to environmental stressors, particularly cold and vibration, is heavily modulated by their personal, biological, and behavioral factors.
What kind of factors?
The source materials explicitly note that the use of tobacco, alcohol, and certain medications drastically alters the risk profile.
Let's follow the biology on that. How does smoking a cigarette fundamentally change a worker's ergonomic resilience?
The mechanism is entirely vascular. Nicotine is a highly potent systemic vasoconstrictor.
Yo, right.
When a worker smokes, it chemically forces their blood vessels to narrow. Therefore, a smoker's baseline blood flow to their extremities is already chronically compromised before they even step foot on the job site.
Wow. So if you take that worker and you expose them to hand-arm vibration, which traumatizes and collapses capillaries, and you put them in a cold environment, which triggers further autonomic vasoconstriction,
They're at a staggeringly higher risk of developing Raynaud's phenomenon, nerve damage, and tendinitis compared to a non-smoking colleague performing the identical task.
the personal lifestyle factor acts as an accelerant to the occupational exposure. That is a brilliant synthesis of the variables. It demonstrates how occupational safety cannot exist in a vacuum.
It has a look at the holistic physiology of the human being.
Okay, what about the ambient atmospheric stressors like lighting and noise? At first glance, I evaluate lighting as a vision issue or a slip and fall hazard. I don't naturally categorize a dim light bulb as an ergonomic threat.
It originates as an optical issue, but the body's response immediately transforms it into a severe postural hazard.
How so?
Human biomechanics are deeply subservient to our sensory organs. We rely primarily on vision to gather information and guide our physical actions. If a workstation is poorly illuminated, or conversely, if bright overhead lights create a blinding glare on a computer monitor.
The worker cannot clearly resolve the visual details of the task.
Right. And because the worker can't see, their body physically adapts to solve the optical problem. They lean in.
They subconsciously sacrifice their skeletal alignment to compensate for the poor visual environment.
Exactly. They crane their neck sharply forward, pulling the heavy skull off its center of gravity. They hunch their thoracic spine. They twist their torso to view the screen from an angle that avoids the glare.
Inadequate lighting forces the worker to abandon a neutral posture and lock themselves directly into a highly damaging, static, awkward posture.
The visual cortex demands a clear image, and the musculoskeletal system will endure immense structural strain to provide it.
That is a phenomenal way to frame it. The visual cortex demands clarity, and the spine pays the price. And what is the mechanism behind noise? We know loud noise causes hearing loss, but how does the ambient sound of a factory floor alter the biomechanical equation?
High ambient noise functions as a dual threat stressor, acting simultaneously on the psychology and the physiology of the worker.
The texts talk about psychosocial stressors, right? Factors like machine-paced work speed, monotonous repetition, high cognitive demand.
Yes, and noise is a massive contributing factor there. Excessive noise is deeply annoying, it shatters concentration, and it severely degrades verbal communication.
Which means, returning to the posture issue, workers have to lean in closer, twisting their bodies just to hear instructions from a colleague.
Yes, it induces awkward postures for communication. But physiologically, chronic exposure to high noise levels triggers a continuous low-grade fight-or-flight response in the autonomic nervous system.
So it elevates resting heart rate, increases blood pressure, and crucially, it elevates ambient muscle tension throughout the body.
When a worker's baseline muscle tension is artificially elevated by stress, they fatigue significantly faster. They are burning vital metabolic energy and generating lactic acid just existing in the noisy space before they even lift a tool or exert any productive force.
Unbelievable. We have now thoroughly mapped the battlefield. We have explored the time variation of repetition, the intensity of force, the mechanical leverage of awkward and static postures, and the compounding environmental stressors of vibration, contact, temperature, lighting, and noise.
The human body is under continuous multi-front assault.
So if I am a safety professional, it is not enough to simply diagnose the breakdown. I am paid to fix it. What are the essential skills and tools I must demonstrate to pass this section of the ASP exam and actually protect the workforce?
The essential competency is the transition from identification to application and control.
Application and control.
The certification exam will rigorously test your ability to take these dense theoretical biomechanical principles and practically apply them to physical workspace design and manual material handling.
Because it is insufficient to observe a worker and subjectively declare, that looks difficult.
Exactly. The safety professional must systematically quantify the hazard using standardized metrics and then engineer a solution.
Let's open up the safety professional's toolkit. How do we systematically evaluate a workstation on the ground?
The foundational tool is the ergonomic checklist. Safety professionals utilize highly specific, standardized analytical tools to systematically evaluate the physical demands of the work, the geometric layout of the station, and the physical characteristics of the loads being handled.
You are methodically scanning for the red flags. Like, are the elbows elevated above mid-torso? Is there excessive reaching beyond the immediate safety zone? Are the wrists deviated?
Yes, checklists keep it objective.
And when it comes to manual material handling, which is arguably the largest source of severe paralyzing back injuries in the workforce, the absolute gold standard referenced in the ASP blueprint is the NOS lifting equation.
Yes, the NOS lifting equation is critical.
This isn't just a guideline, it is a complex mathematical formula. Let's walk the listener through exactly how this works.
The National Institute for Occupational Safety and Health developed the lifting equation to scientifically quantify the biomechanical risk associated with two-handed manual lifting tasks.
And the ultimate output of the formula is what is called the recommended weight limit, or RWL, right?
Correct. The RWL tells you the maximum weight a healthy worker could lift under that specific set of postural and environmental conditions for an entire shift without an increased risk of lower back injury.
So how does the formula actually calculate that? I mean, it has to take into account all the awkward postures and repetition rates we just discussed and turn them into math.
It does. The formula starts with a load constant of 51 pounds, which is the absolute maximum weight anyone should lift under perfect ideal conditions.
Okay, 51 pounds is the starting point.
Then it multiplies that 51 pounds by a series of 6 variables, each represented as a fraction between 0 and 1.
So if a variable is perfect, it equals 1, and the weight limit stays high.
Exactly. But if a variable is poor, the fraction decreases, which drastically lowers the final recommended weight.
Let's invent a scenario to make this concrete. I am evaluating a worker lifting boxes off a pallet. What is the first variable the equation looks at?
The first is the horizontal multiplier. How far away is the load from the worker's spine?
Because the further you reach your arms out to grab the box, the longer the lever arm becomes.
And the exponentially greater the torque placed on your lumbar discs. If the box is held tight against the stomach, the multiplier is near 1.0.
But if the worker has to reach out, say, 25 inches to grab it?
Then the multiplier drops to 0.4, instantly cutting the safe lifting limit by more than half.
Wow. What are the other variables?
We measure the vertical location of the hands at the start of the lift. Lifting from the floor is highly dangerous, whereas lifting from knuckle height is ideal.
Makes sense.
We also measure the distance the object travels vertically. We calculate the asymmetry multiplier, which mathematically penalizes any twisting or torsional rotation of the spine during the lift.
The wet towel effect we talked about earlier.
Exactly. We factor in the frequency, how many lifts per minute, and finally, the coupling multiplier, which evaluates how good the handhold is. Are there solid engineered handles, or is it a slippery, awkwardly shaped object?
So you multiply the 51-pound base by all these fractions, and the formula spits out the recommended weight limit, the RWL.
Yes, that gives you the safe weight limit.
But that is only half the equation, right? How do you determine the actual risk level for the worker?
Once you calculate the RWL, you compare it directly to the actual physical weight of the object the worker is trying to lift. We call that the load weight.
Okay.
This comparison yields the lifting index. The formula is simply the load weight divided by the recommended weight limit.
Let's run the math on our hypothetical worker. Let's say the box he is lifting actually weighs 60 pounds. That is the load weight.
Right.
But because he has to reach far out to grab it, and he has to twist his back to set it on a conveyor belt, your IOH calculation determines that the recommended weight limit for that terrible posture is only 15 pounds.
Okay, so you divide the load weight of 60 by the RWL of 15.
Which results in a lifting index of 4.0.
Exactly.
And a lifting index of 4.0 means what, in practical terms?
It means the situation is critical. A lifting index of exactly 1.0 indicates a baseline risk where most healthy workers can perform the task safely.
So anything above 1.0 is bad.
Any index greater than 1.0 indicates that the task poses an increased risk for lifting-related lower back pain. A lifting index of 4.0 means the worker is being forced to lift 4 times the mathematically safe limit for that specific biomechanical posture.
4 times the safe limit. At that index, the risk of a catastrophic disc herniation is imminent, and immediate engineering interventions are mandatory.
Mandatory. This quantitative data is the output of an occupational exposure assessment. The purpose of these assessments is to systematically measure the duration, frequency, and magnitude of exposure.
But collecting the data is just the diagnosis. Once you know the lifting index is 4.0, or you measure that the finger repetition rate exceeds safe limits, what are the tools to actually neutralize the hazard?
This is where we implement ergonomic controls based on the hierarchy of safety. The paramount objective is always engineering controls.
We want to physically redesign the work environment to eliminate the hazard at its source, removing human behavior from the equation.
Precisely. For example, to eliminate the severe horizontal reaching that ruined our lifting index, we redesigned the physical workstation. We implement a rule that all frequently accessed tools and materials must be located within a 15-inch radius of the worker.
We bring the work to the human, not the human to the work.
Yes.
And what about managing the working heights? We talked extensively about the slow torture of static muscle contraction when desks or benches are the wrong height.
Adjusting working height is an incredibly effective engineering control. The physical height of the bench dictates the postural demands placed on the head, neck, back, and arms.
Right. If a workbench is too low, the worker's spine is flexed forward into a state of continuous static strain.
And if the bench is too high, the worker must statically elevate their shoulders just to reach over the surface. The texts provide a highly testable, specific guideline for this scenario.
Oh, this is perfect for the ASP candidates. What is the guideline?
If a worker is performing standing work that predominantly requires the exertion of upper body strength, such as heavy mechanical assembly, or pressing downward on a tool, the bench height should be engineered to be precisely 2 to 4 inches below the worker's resting elbow height.
2 to 4 inches below the elbow. The mechanical reason for that is leverage, right?
Yes.
By lowering the bench just slightly below the elbow, the worker can lock their arms and use the heavy weight of their entire torso to press downward, letting gravity do the work, rather than relying solely on the smaller, weaker muscles of the shoulder and arm.
Exactly. It optimizes mechanical advantage. Another critical engineering control is proper tool selection.
Like what?
Well, to mitigate mechanical contact stress, we mandate tools with contoured handles that eliminate sharp edges or pinch points digging into the palm.
And what about that intense finger repetition?
To mitigate forceful gripping and extreme finger repetition, we replace single-finger trigger tools with tools utilizing large, elongated paddle switches that allow the worker to activate the tool using the combined strength of all 4 fingers simultaneously.
Or even proximity sensors that require absolutely zero physical force to activate.
Even better. And to combat white finger disease, we specify tools with advanced internal dampening mechanisms, and we wrap handles in vibration-absorbing materials to isolate the destructive energy before it enters the hand.
So those are engineering controls, altering the physical geometry and equipment. But in reality, you cannot always engineer every single hazard out of existence. Sometimes a heavy part simply has to be manipulated by hand.
That's true.
When engineering falls short, what are the administrative controls, the work practice changes we can enforce?
Administrative controls don't change the physical environment. They change how the humans interact with it. Job rotation is the primary administrative tool.
How does that work in practice?
If a specific task requires an intense, high-frequency repetition of the right shoulder, the safety manager implements a schedule where that worker rotates to a completely different task, perhaps one requiring lower body movement or visual inspection halfway through the shift.
By rotating the worker, you are directly manipulating the duration and frequency multipliers in our risk equation.
Giving the inflamed shoulder tissue the crucial hours it needs to clear metabolic waste and repair micro tears before it fails.
The source material also touches on more modern interventions, like early symptom reporting programs and the use of exoskeletons.
Early symptom intervention is the final safety net. Because cumulative trauma disorders develop slowly over months or years, catching the microtraumas in their infancy is vital.
Right. If a worker is encouraged to report a mild tingling or a slight ache early on, the safety team can perform an ergonomic assessment and adjust the monitor height or change the tool grip long before the inflammation escalates into permanent nerve demyelination.
And exoskeletons represent the cutting edge of physical intervention. They act as wearable engineering controls.
Oh, that's a cool way to look at it.
These mechanical frames physically bypass the worker's biological joints, transferring the heavy compressive load of lifting directly through the external frame and into the floor, preserving the worker's spine.
If you synthesize everything we've discussed, it becomes clear that the ultimate role of the safety professional is not reactionary. It isn't just running around buying expensive lumbar support chairs or handing out wrist splints after half the department has already filed injury reports.
No, not at all.
It is what the literature refers to as proactive ergonomics. It is the ability to foresee these biomechanical clashes and engineer the hazard completely out of existence during the initial planning stages.
Yes, the safety professional must integrate with the architects, the industrial engineers, and the facility planners before the factory floor is even poured, ensuring the geometry of the space inherently respects the limitations of human anatomy.
That is the pinnacle of occupational health management. It is a profoundly human-centered approach to industrial design.
You ensure that the foundational selection of tools, the sequencing of job methods, and the geometric layout of the workstations will impose zero undue stress, static strain, or excessive force on the vast majority of the workforce from the very first minute of operations.
We have covered a massive expanse of technical and physiological ground today on ASP Exam Domain 3, Topic 2. Let's execute a detailed recap to solidify these concepts for the ASP candidates and the curious listeners alike.
Sounds good.
We systematically analyzed the 4 main ergonomic risk factors. First, we defined repetition as the time variation of a musculoskeletal load, exploring how cyclical movements deny tissues the necessary time to clear acidic metabolic waste, and how repetition acts as an aggressive amplifier for all other hazards.
Second, we examined force, evaluating the physical exertion required to overcome environmental resistance. We highlighted the counterintuitive glove effect, where severed tactile feedback causes the central nervous system to panic and increase grip force by up to 28%.
Third, we dissected awkward and static postures. We established that deviating from a neutral, mechanically advantageous joint alignment geometrically stretches tissues and plummets force tolerance.
And we explored the deep cellular irony that static holding, simply sitting rigid at a desk, can cause faster, more painful muscle fatigue than dynamic labor because the continuous muscle contraction acts as an internal tourniquet, clamping off blood flow and pooling lactic acid.
Fourth, we navigated the environmental stressors. We looked at the vascular devastation of hand-arm vibration, which collapses capillaries, causes white finger disease, and triggers a subconscious overgripping reflex.
We discussed whole body vibration acting as a slow-motion jackhammer on the spinal discs of truck drivers. We explained how ambient cold triggers localized vasoconstriction, robbing muscles of oxygen and forcing them to work harder.
A physiological risk that is heavily compounded by personal lifestyle choices, like the vasoconstrictive effects of nicotine. And we revealed how poor lighting and excessive noise force the body to adopt structurally compromised postures just to see and communicate, elevating overall ambient muscle tension.
And finally, we synthesized these theories into the practical skills required of the safety professional. Deploying structured ergonomic checklists, executing complex mathematical analyses like the IOH lifting equation to calculate the precise lifting index, conducting rigorous exposure assessments.
And ultimately implementing proactive engineering controls like designing bench heights, specifically relative to elbow height, to physically eliminate the hazard. Mastering this material is about far more than memorizing the variables of a lifting equation to pass 8% of a certification exam.
It really is.
It is about developing the vision to recognize the invisible, slow-moving biomechanical forces that grind down the human machine over a 30-year career. It is about actively preserving the long-term physical mobility, the comfort, and the dignity of the people relying on your expertise to keep them safe.
That is the true impact of the discipline. The scientific knowledge applied here directly intercepts the trajectory of chronic pain and lifelong disability.
As we conclude this session of QHSE Talks, I want to leave you with a final provocative concept to examine in your own workplace. In the realm of occupational safety, we spend an inordinate amount of time trying to modify human behavior.
We really do.
We constantly instruct workers to use proper lifting technique, or be mindful of your body mechanics, or make sure you sit up straight. We cover break rooms with posters reminding them to bend their knees.
Yeah, posters everywhere.
But based on the physiological and biomechanical realities we have explored today regarding neutral postures, the devastation of static muscular loads, and the compounding effects of environmental stressors, if the physical, structural design of the workspace fundamentally forces a human being to adopt an awkward, twisted, statically loaded posture just to reach the tools they need to perform their duties, is an eventual musculoskeletal injury truly a behavioral failure on the part of the worker? Or is it an engineering failure on the part of the designer? Think deeply about that the next time you find yourself trying to adjust your office chair, or the next time your shoulders ache after a long, seemingly uneventful shift.
It is a question that challenges the foundational assumptions of labor, and it defines the very core mission of modern ergonomics.
Thank you for dedicating your time to join us for this rigorous exploration into the mechanics of work and the resilience of the human body. We will see you on the next session of QHSE Talks.